Quantum information is the science that exploits the laws of quantum mechanics to enhance our communication and computational capabilities. Future quantum devices will allow to perform complex tasks not accessible to classical computers and fundamentally secure transfer of encrypted information. At the University of Sheffield, a team of researchers is working to develop a computer processing unit combining the quantum nature of light and novel semiconductor technologies. The foundation of this technological step change is the quantum bit, or qubit, as the unit of quantum information is known. While a classical bit can only be either 0 or 1, a qubit can be 0 and 1 at the same time and is said to be in a superposition state of the two. The 1 and the 0 of the qubit can be represented by the spin-up and spin-down states of an electron in a wire, or by the spin states of the nucleus in an atom, or by the polarization state of a photon. The main advantage of qubits with respect to classical bits can be understood by visualizing the computation as a journey from A to B in a complex landscape. A classical bit must stick to the roads representing the classical values 0 and 1. 0, 1. Qubits, however, are a superposition of 0 and 1 and can therefore take a shortcut through the computational landscape. For this reason, the computation requires fewer steps and can therefore be faster. Among all the different physical systems which can be used as qubits, photons have the advantage that after having performed a calculation, they can also share the result at the speed of light, allowing fast and long-distance communications. For these reasons, researchers at the University of Sheffield are developing new photonic devices combining different chemical elements such as gallium, arsenic, aluminium and indium. These materials, called 3-5 semiconductors, are particularly suitable for photon manipulation and are processed in the advanced laboratories of the National Centre for 3-5 Technologies. The simplest possible quantum circuit with photons requires three key components: sources of single identical photons, a beam splitter, and single photon counters. Single photon sources are implemented using quantum dots, nanostructures able to trap one electron and one hole. When the electron falls into the hole, a photon is emitted. Trains of identical photons can be obtained by repeating this recombination process in a controllable way. The beam splitter is implemented using two wires that guide photons close together, allowing them to interfere. In this way, taking advantage of the Hong-O-Mandel effect, several different logical operations can be performed. Single photon counters are implemented by means of superconducting nanowires. These devices are so sensitive that they are able to detect a small change in the electric current caused by the arrival of a photon. In this way, it is possible to count how many photons arrive from each arm of the beam splitter and read out the result of the operation. These three components integrated together constitute the core of a scalable platform for a quantum chip based on light. Such a platform, not dissimilar to present electronic circuits, offers extraordinary computational possibilities and can also be used as a node to securely distribute encrypted information over long distances.